We proved that, so recall what we have done is that home VW, where V and W are finite dimensional vector spaces. In that case, home VW is also a finite dimensional vector space. And this is the set actually of all vector space homomorphisms of V W. Then we defined this home VF, and this we also have denoted by V hat. This is the set of all vector space homomorphisms of V into F, where F is treated vector space over itself. And if V is of dimension M, then V hat is also of dimension M, and this is called the dual space of V. We also have defined the second dual, that means dual of dual. So this is called here, this is F, F. This is called your second dual space. And if dimension of say V over F is M, and dimension of W over F is N, both are finite, each of these is a finite dimensional vector space over F. We also know that particular the dimension of home V W is Mn, and this also is finite. And the dimension of V over F, dimension of V hat over F, dimension of V hat over F, all of them are equal and equal to M. And so V is isomorphic onto V hat, which is also isomorphic to V hat, and this second dual. And this V hat. And in particular, this gave that V is isomorphic second dual. And this one such map we also obtained. And recall the map. So the map was V to V hat, which is say psi. So psi goes V to the map TV. Now TV here is a map V hat to F. So V hat consists of your homomorphisms of V into F, let us say F, and this goes to F of TV, and this we have defined that this is TVF, and TVF is F of V. Now this F of V because f is since f is from v to f, v goes to v of f or f of v. So f of v is a scalar. And we had proved that this is actually an isomorphism. Is an isomorphism. Okay, so the basis also we have proved that if B is a basis, let us say V1, V2, say Vn or Vm, whatever it is a basis, is an ordered basis. Ordered basis means we are prescribing this basis for V over F, then we get an ordered basis for V hat over F, namely the hat consisting of V1 hat, V2 hat, and these are Vn hat, where these, to recall this Vi under Vj hat, this is delta Ij, that means that this is 1 when I is equal to j and 0 when I is different from j. That's how they were defined. So similarly, we can have a basis ordered basis. These Vi hats are of course here in B hat, a B hat, hat, and these we can denote by putting twice the hats. Vn hat for V hat over F, and such that you can see that this Vi hat under Vj hat delta J for all Ij 1 to n. So this gives rise to a basis for this second dual also over F. Now we have seen that if V is finite dimensional, V hat and V hat dual and second dual, both of them are also finite dimensional. In fact, all the three are isomorphic. That's what we have seen, and are of the same dimension. Now we look for the subspaces of V hat or V hat hat. So let us take V be finite dimensional, and we define here for say subspace W of V. So let us take VFB a vector space, and we take W to be a subspace of V. Now define the annihilator of W, say annihilator of W for F. This is the set of all vector space homomorphisms from V into F, that means the elements in the dual space, which are killing every vector here of W. So this is a subset here of V hat, because this consists of those elements of V hat which annihilate every W in W. Now what we can prove is that this is in fact is a subspace. Annihilator here of W is a subspace of. So for this you can prove, let us take that this is closed with respect to, because V hat is a vector space that we know. So for a subset to be a subspace, we need to verify it is closed with respect to addition and is closed with respect to scalar multiplication. So let us take Fg here in annihilator, and let us take this alpha in F. Then F plus G and alpha F plus G and alpha F are vector space homomorphism of V into F, so they are in V hat. Further, you can see that F plus G on V, because they are vector space homomorphisms, and how the sum of the two homomorphisms T1 and T2 is defined. T1 plus T2 acting on V is T1V plus T2V. G. And also alpha F of V is same as alpha F. So if W is in V and he, sorry, if F, so if since F is in annihilator of W, then what happens is Fw is 0 for every W in W. Similarly, GW is also for every W in W. So what we get is F plus G, F plus G of W, same as Fw plus GW, and it's 0 plus 0. And that makes that F plus G is in here annihilator. Annihilator here of W over F. This happens for us. And alpha F of W is equal to 0. That also makes that alpha F is also annihilator of W. Hence, this is a subspace. Okay. So this is a subspace. You can also see that if you have also let us take W1 is contained in W2, and W2 is a so are subspaces here. Let us take that W1, W2 are subspaces of a vector space V or F. Then annihilator of let us take say W1 and annihilator of W2, annihilator of W2 are subspaces of V hat. Moreover, it is easy to see that annihilator of W1 contains annihilator of W2. So inequality reverses actually. So this is easy to see because if any element is if there is an element here, say F in the annihilator, so it annihilates every vector in W1. So in particular, it also annihilates every vector of W2 because every vector in W2 is here. So it reverses the inequality. We also would like to prove the following theorem. So, let us take that V is a finite dimensional vector space over F. W is a subspace of V. Then what happens is about say W hat. This is a vector space and is a subspace of V hat. And this is actually isomorphic onto V hat by AW, the quotient. In particular, we can also see the dimension, that the dimension of the annihilator AW here for F is the difference of the dimension of V minus the dimension of, where AW means annihilator. Of W. So what we want to prove is that if V is finite dimensional vector space over F, so W is subspace of V, so W is also finite dimensional. In that case, W hat is a finite dimensional vector space, and we shall prove that the dimension of the annihilator is actually dimension of V minus dimension of W. And for doing this, what we prove is that W hat is isomorphic to V hat over A W. Okay, so let's take the proof. So what we can see is here as follows. So we want to use this first isomorphism theorem of vector spaces, and we'll try to have a map from V hat onto W hat with the kernel AW, and then we can apply this. So for the proof, what we do is therefore we shall have a map here. So we shall have a map. Here from V hat to W hat. Now, what this consists of, let us say this is T. So, V hat consists of the homomorphism V into F. So, this goes to say F of T. Now, F of T should be a homomorphism of W into F of T. So, this let us take that this is the restriction here of F on W. So, where this FW is the restriction of F on W. That means what? FW is same. So FW of V is same as F of V for every V belonging to W. So if the domain element is in W, in that case, F and FW both are same. Okay. Now, one can see now what we have here, this map. So, what is the map? Recall the map T is V hat to W hat. And how we are mapping F to F T as F of W. The restriction here, F restricted to W. Now, this map is well defined. You can check that this FW is actually in W hat. So you can easily prove, you can see that this map is well defined, is well defined. So if you have so if you want to prove that this FW is in W hat, that means F of W and W1 plus W2 are two elements. In that case, W1 plus W2 belongs to W because W is subspace and W1, W2 come from W. So this is same as therefore F of W1 plus W2. Now F is a homomorphism of V into F and therefore it results the sum FW1 plus FW. Now whenever the domain element is in W, this is F and FW are same. Similarly, you can see that FW alpha W is the same as alpha F W W for every W in W for every W1 W2 in W. So that makes that FW is in home WF. That means this hat. Just a second. Okay, you can also see that if f and g are equal, in that case, your f and g under t are also equal. Their images also are equal. So the map is well defined. That is easy to see. Now, what we want to make use of is that T is a homomorphism of V hat into W hat, and its kernel also we shall show that is actually the annihilator, and that will do the job. Okay. Now, T, the map V hat to W hat, and that takes F to F of F under T as the restriction of this FW. Restriction of F on W is a homomorphism, is a vector space homomorphism. For this, we need to prove number one, that it preserves the sum, and it preserves scalar multiplication. So for T preserves sum, T preserves the scalar multiplication. So for this, let us take F and G. They are in V hat, and alpha is an element here in F. You can observe that F plus G under T is the restriction here. F plus G to W is same as F restricted to W plus G restricted to W. This is, you can see that this, and therefore this will become equal to F of T plus G of T. Now this for checking this, so what you, for this what you do is that you take this, let us take W in W, then F plus G of W is same as FW plus GW, because that's how the sum of the two homomorphisms are defined. Now FW here. So when you take this, so this makes that when you restrict, because F plus G restricted to W, so this is F plus GW is same as F plus G. So it's same as under W, this is same as F plus G W. This is FW plus G W. Plus W is in W. W is in W. And this, of course, is FWW plus GWW. So what you see here is that this makes that F plus G is T is same as FT plus GT. And similarly, you can also check that this alpha F of T is same as alpha times Ft. It's same as alpha times F under T. So once again, we use the same thing, that this alpha F of T is defined as the restriction of alpha F on W. Since the restriction of the left hand side is the restriction of this on W is same as alpha times restriction of F on W. So these two together will prove that T is a homomorphism and C is a homomorphism. Now T is a homomorphism and it is onto also. We can prove this that T is onto. Further, T is on. T is onto. So this is T is V hat onto W hat. So for this, let us take one element, say H, here in W hat, and we want to find out an element. So we find an element F in V hat such that this F under T is H. That is an F. That is, there exists an F in V hat such that F restricted to W, that is FW, is same as H. Okay, that means there is a homomorphism F in V hat which on W coincides with H. That's what it means. So now for this, what we see here is that W is also finite dimensional now. Recall dimension of V over F is, let us take this as N, is finite. This makes that the dimension or F of W, say M, is also finite. And we also know that M cannot exceed N. Okay. So let us take a basis now for W over F. So let us take this B W, which consists of, say, W1, W2, and let us say Wm, be a basis for W over F. Now we know that we can blow up this BW, the set of linearly independent vectors in V, so that we get a basis for V over F. Now blow this BW, the subset of V over F, to a basis B for V over F. That is, there exist vectors. Let us take V1, V2, say Vr in V such that B, so these vectors W1, W2, Wm together with V1, V2 and this is R is a basis for V over F. Naturally, this N becomes M plus R. So we blow a basis here, say BW of W, to a basis B for V over F, and that retains naturally all these vectors from the basis BW. So basis B for V over F is W1, W2, Wm, and some more vectors if required, V1, V2, Vr, so that all of these together, M plus R elements, form a basis for V over F, and therefore N has to be M plus R. Now what we can see here is that this if let us take W1 is the subspace spanned by Let us take V1, V2 and say VR. Subspace of V over F spanned by V1, V2, R. Then what we can see is that V is actually the direct sum of these two subspaces. For every vector V in V can be uniquely written as V equal to alpha 1 W1 plus alpha 2 W2 plus alpha M Wm plus beta 1 V1 plus beta 2 V2 plus beta R VR, where alpha is beta j's are uniquely determined from F for a given B. So since they are uniquely determined, and therefore this element, of course this is in W, and this element, this is in W1, so this becomes their internal direct sum because of the uniqueness that will make that this is contained here. So that is for every V in V. Therefore, V is contained in internal direct sum, external direct sum. That's isomorphic, and therefore we shall not distinguish. So this is contained here in the direct sum of W and W1, and the sum of two subspaces is always a subspace of V, and that proves that the two are equal. So W plus W1. So V is the direct sum of W and W1. Nice. So what we want now? So what we want is that H. So what is now? So H belongs to W hat, and so we define this now for every H and H. Define here F in V hat by the following as follows. Okay. So for V in V, for every V in V, what we can write this as uniquely, there exists W in W and unique W and W1 in W1, such that this V is equal to W and plus W1. Okay. Now this is unique. So there is a unique W in W and there is a unique W1 in W1, such that V is equal to W plus W1. So we define now here that this f of V is HW. So f of V as HW. So what is the map? Map is FV is equal to HW, where V is W plus W1. Now you can check that this F is a vector space homomorphism of V hat, and this is the restriction of F on H. So define the homomorphism here in V hat as writing this, so we need to know what is the images of P vector V in V under F. So we are defining this FV as F of W plus W1 as HW. You can prove that this F is in fact in the hat. So to show this that F is in V hat, you can take F with this F belongs to V hat. Recall that how this F is defined, that F of V is F of V plus W plus W1. This is here H of W. That is how the map is defined. W. Okay. So V and V prime, suppose V and V prime, they belong to V hat. Is there exist uniquely W and W prime into W and W1 and W1 prime into 1 such that W is W plus W1 and sorry, this is V. And V prime is W prime plus W1 prime. But then how the map is defined, so this is F of V plus V prime. This is F of W plus W1 plus W prime plus W1 prime. Now this is F W plus W prime plus W1 plus W1 prime. Now this is an element of W1. This is an element of W. And the map is defined that this is same as HW plus W. Now H is in W hat. That means this is a homomorph. This is HW plus HW prime. HW we have defined this to be F of V, and this is defined as F of. So it preserves the sum, and similarly you can also prove that F of alpha V is same as alpha F. So this makes that F is in, so what we have got, F is in V. And the way we have defined, and H therefore defined in this way, so F defined this way, so this H becomes then F of T. This is the restriction of F on W. So what we get is has T is on T is V hat on to W. So we have got a homomorphism. So we have a vector space homomorphism T V to V hat to W hat is a vector space homomorphism of V hat on to W hat. You can also see what is the kernel. The kernel of T is what? It consists of all elements here F in V hat such that f of t is 0. F of t is 0. Okay. And what is f of t? What is f? Ft, how the map is defined now. This is your f of t. This is 0. The map T defines f goes to the restriction of f on W. The map takes f to how the f under T was f W. Restriction of f on W. This is f in V hat such that f restricted to W is 0. F restricted to W is 0 means what? This is the set of all f in V hat such that f of V is 0 for every V in W. You recall what is the definition of the annihilator of W? That it annihilates every vector from W. So this is the annihilator of F. So this is the kernel. Hence, kernel of T is this. Hence, by the first isomorphism theorem, what we have got is that V hat divided by the kernel T isomorphic onto W hat, or that means that V hat by the annihilator, that is AW, is isomorphic onto. Now, V is a finite dimensional. Now, V is finite dimensional. V over F is finite dimensional. This is N is finite dimensional. Dimension of W over F is M, is also finite dimension. So what we have got is therefore the dimension of V hat over F. This is also N and is also finite dimensional. And the dimension here, so this also will imply that so this will also imply, because W, so here this annihilator is a subspace of V hat. So dimension of this annihilator, that means AW over F, is also finite, and this cannot exceed N. It is also finite. So everything here, W hat also finite dimensional, and dimension of W is also finite. Dimension of W hat and the dimension of W, they are also same. So the isomorphism of V hat by annihilator W isomorphic to W hat makes both sides are finite dimensional. So dimensions are equal. V hat by annihilator of W over F is same as the dimension of W hat over F. Now you can see that this is the dimension of V hat over F minus the dimension of annihilator of W over F is same as dimension of W hat over F. Now dimension of V hat is same as the dimension of V over F minus the dimension of annihilator over F is same as dimension of W hat is same as dimension of W over F. So this makes that the dimension of annihilator of W over F is, you take this on this side and this on this side. So this dimension of V over F minus the dimension of W over F. So the dimension of the annihilator of W is the difference here. So the dimension of V over F, if it is N and if it is M, so this is the dimension. So R is the dimension of the annihilator, N minus M. So what we have proved is if V is a finite dimensional vector space and W is a subspace of V, in that case W hat becomes isomorphic onto V hat by annihilator W, and in particular this gives us that the dimension of the annihilator is same as the dimension V minus dimension W. And as a deduction from here, you can prove before that. So once we have a vector space and we have a subspace here, so what we have got is that annihilator here of W, AW is a subspace of V hat. Now this is a vector space. So once again you can do that annihilator. Now V hat is a vector space. So annihilator of W is a subspace of V hat. That means second. So this is a subspace here, and in fact, what you can see is that this W is isomorphic to annihilator of W. Now this I leave for you. In case this, of course, everything is for finite dimension, where W is a subspace of V and dimension of V over F is finite dimension. So this I leave for you, that this isomorphic onto this. And we simply, because of then they become of the same dimension, so we simply write instead of the isomorphism, that is AAW. So this is what it is. Now we shall discuss an application of this annihilators, sum of equations, but that will be next time. So thank you very much for your kind attention.
Thank you, sir.